electric train.
What is it? How does it work?
I don't know about it. We have been researching for a big while. And if you want to know more about it, follow us.
Okay.
Hi! So we're going to show you about our apparatus that we use. So the first one is bare copper wire with 1 millimeter diameter.
What's next?
3H PVC pipe.
And alkali battery.
And we use a drill to make a car.
So the last one is
The last important, neodymium magnet.
How was it?
I love it! Oh my god!
Oh, you really are!
Yes! How does it work? I don't know about it.
Now we're going to talk about the mechanism. Why does the train work? I have a battery and 2 neodymium magnetic. I put one magnetic on the positive side and I put the other one on the negative side. Then I will let the magnetic touch the coil. This way, the electron from the battery will come flow through the coil. That make current.
When there is current in the wire, it induces the magnetic field. In this direction, from the equation F equals to current times with the length of the wire crossed with the magnetic field. So our battery will be pushed by the magnetic force in this direction.
So when you got this and you put this into the coil, be careful with the sparks. But it's alright, it's not that much. So your magnets have to be in the right orientation or else the magnetic force will be in the opposite direction to the magnetic field.
We move back to the basic electric field concept. The positive charge will flow in the same direction of the field, and the negative charge will flow in the opposite direction to the field. In a magnetic field is very similar. The north magnetic pole will be pushed in the one direction and the south pole will be pushed in the other direction. If the magnetic field is not the same all over, it's called non-uniform magnetic field. You might feel a slightly bigger push on the north pole than on the south pole of the magnet. And that's what's actually happening here. The magnetic field is created by the current is strongest in the middle and then it spreads out and it becomes weaker at the end. In this case, we use the same coil, which means the direction of the coil is not changed. And because of the battery, we have electrons flow in the coil. When there's electron flowing, there are electric current and the induced magnetic field in the opposite direction to electron flowing.
From this equation, electric force equals to current times with the length of the coil that crosses with magnetic field. In this case, the induced magnetic field. This electric force drives our battery to move.
As I told you that, we use the same coil, so we've got only two variables here. They are the direction of battery and magnetic poles. Because of these two variables, we have four situations to study here. The first one is south pole on the outside, and the positive side of the battery is on the left. B. The induced magnetic field is in this direction. The battery is pushed out of the coil. The second is South pole on the outside, but this time, the positive side of the battery is on the right. B. The inducted magnetic field is in this direction. The battery is pushed into the coil. The third is North pole on the outside. The positive side of the battery is on the left. B. The inducted magnetic field is in this direction. The battery is pushed into the coil.
Here comes the last one. North pole on the outside and the negative side on the battery is on the left. B. The induced magnetic field is in this direction. The battery is pushed out of the coil. This happens because in every situation we have two different sources of magnetic field. One is induced from current and one is from our neodymium magnet.
How can we know that which way our battery is going to move? We have a little talk here about the nature of magnetic field. The magnetic field lines emerge in the North Pole and merge in the South Pole like this. When the induced magnetic is in this direction and our magnets are in this arrangement, north-south, south-north, the total life of magnetic field will be like this.
In this picture, our battery will be pushed and then move in this way. If you take a look of this line at the North Pole of each, on the right hand side, all the lines are in the same direction, but the other one is not. So, we can easily see that on the right they enhance each other, but on the left they confuse each other. Because of this reason, our battery will be pushed in this direction.
We use that concept as the model of the last T situations. Here are the differences.
Now I know the mechanism of it and I apply it in the model. Yes, it is.
For the applications, at the very first time that we've seen this, we thought that what will make train from this concept? We have learned that we can make an electric train above two coils attached to each other like this. We found that it's slower than running in the tunnel. But if we continue this kind of prototype to make a huge one for the real transportation, we don't need to coil the big diameter tunnel up. Instead, we coil the smaller one, but like 10 or 20 coils. And we can reduce the risk of the sparks danger that can occur a huge accident to our passengers or the thing inside the train. The driving force of the train is from the electricity, like from the electric energy. There's no carbon dioxide producing while the train is running, so I can say it's quite cleaner than we used oil to be the fuel.